Hi everyone, this is Kantil Patel. I am presenting the project implementation for CS809. The title of the project is Multi-Agent Pathfinding on the GPU using ComputeShader. So let's start with the overview of presentation. Introduction to GPGPU, General Purpose Graphics Computing Unit ComputeShader. Uh, then we will look into the related research discussion, the work that has been done by the researchers earlier on the same topic. Then we will look into some important concepts that are that will be helping us to understand the implementation. Then we will discuss the approach that we are using in detail with the implementation, and later we will look into the real-time rendering pipeline for multi-agent system, where we show how we render thousands of agents together in the scene, and at the end we will sum up the results that we have got and compare it with the previous published work, and finally we will conclude the project output. Now, introduction to GPGPU computer shader. Now, before we start looking into the implementation, it is important to understand what is direct compute for those who are not aware of this technology. So the direct compute allows this high-speed general purpose computation on GPU via compute shader. Now the compute shader are code or a programming API that expands Direct3D 11 beyond graphics programming. Now generally until now we know Direct3D as an graphics programming language, but since Direct3D 11, Compute Shader has been introduced and it has been expanded to be used for general purpose computing. Now the Compute Shader are programmed using HLSL shader language, and it is high level shader language, and the specific model which supports the Compute Shader is shader model 5. Now the Compute Shader is written in the same way as the other pipeline stages are written, like vertex shader, pixel shader, and geometry shaders, but some of the APIs are different for Compute Shader. Uh, Now the very important thing is that single API for Compute Shader across all GPU vendors. Like, so what it means is ComputeShader will work seamlessly on any GPU vendor. It may be an NVIDIA GPU card or an AMD GPU card. But the constraint with ComputeShader is that it only works on Windows operating system, and more specifically it works on Windows 7 and higher versions. So it means that it doesn't support Linux and Mac computers. Now this compute shader can easily interpolate with Direct3D resources like buffer and textures, which are generally used with vertex shaders and pixel shader pipelines. So the output which is taken from a compute shader can easily used by a vertex shader for the rendering purposes. Now we will look into how the GPU programming model works. Now the GPU is distributed with the number of thousand of uh, processors where each thread runs. So direct compute program divides the parallel work into groups of threads. and dispatches multiple thread groups in parallel to solve the problem. That means that a dispatch call from a DirectX API says how many thread groups to be launched. So in this case, on the screen is shown it dispatches the number of thread groups. Now each cell here is a thread group. Now within each thread group there are number of threads here. So this thread group has X, Y, and Z direction of threads. Now in a thread group, each cell represents a thread. So in our ComputeShader program, if we want to identify a particular thread, we could use one of these semantics provided by the ComputeShader API, which is dispatch thread ID, group thread ID, or group ID. Dispatch thread ID is a unique ID assigned to each thread throughout the dispatch call. That means if you consider any of the thread within any of the cell, each thread will be having its own unique ID. Now group thread ID is something which is local to a particular group thread. So a thread having ID of say 1 and 1, which is this cell 1 1, will be having the same ID in the other thread group. So it is unique, the group thread ID is unique to a group thread. Now the other thing, group ID is the integer ID, single ID given to each thread, and it is number in the x direction. So it is like 0, then 1, then 2, then 3, then 4 and 5. So if I want to locate this thread, the ID would be 5. ID would be 5. Okay, next. Now all this thread within a thread group runs concurrently. That means they all executes together. But the thread within different thread groups are not guaranteed to run together, or it may run. It is not guaranteed. So it means that we could provide a same kind of work or same control flow to a particular group in so that all the threads run the same particular job concurrently, but we could give some other different control flow or different work to different thread group. Now to execute a ComputeShader program, we need to transfer some data from CPU to GPU and back and forth. So in DirectX 11, Shader Model 5 was introduced with the new resource types such as read-write buffer, structure buffer, and textures. Now this was specifically to provide support for GPU on DirectX platform. The input resources which are generally read-only resources are bind with shader resource view uh, and which are generally read-only buffers, and the output resources which are read and write buffers are bound with unordered access view. Now these are the different types of objects or data structures that are available in Shader Model 5 to be used with the ComputeShader. So the first one is the read-write type. So in the read-write type data structure, there are read-write buffer, which is probably a raw buffer, and then a consume and append and consume buffer, which is more like a first in first out queue. But in this case we don't have to implement it manually. This has an API like append and consume, dot append and dot consume, so it maintains a counter for you. Now other is the texture read and write buffer, which is 1D, 2D or 3D. Now this is when you want your algorithm to output something into a texture, and you want to use that texture for the rendering purposes in your algorithm. Then there is a read write structure buffer. This is much like in structure array in C++, where you define a structure type and then an array of it. Now this is really useful when we are implementing some complex algorithms where we need to define our data very precisely. Now this is something which is new to uh, ComputeShader Model 5 objects. Now then there are read-only types which are generally used for transferring data from CPU to GPU, which are like buffers. These are created on CPU and populated with the mem copy, and then passed to the GPU. Then there is structure buffer and texture. Now this is a little example of how a computer shader code looks like and how it is executed from DirectX API. Now within the DirectX API, the device context objects has a dispatch call, and the dispatch call takes the x, y and z coordinates for creating the thread grid. Now once this dispatch is called, this compute shader code will execute on GPU or on the specified number of group threads. So in this case the group thread value is 111, which is the only one thread will run within each thread group. Now this is a simple program for addition of numbers in an array. So here there are two input buffers from CPU which are passed on to GPU, which are buffer 0 and buffer 1, and they are structure buffer type. Now another buffer which is buffer out, which is the output from the compute shader, which will be transferred from GPU to CPU so that the CPU can read the processed output. And here is some here in the main method there is a dispatch thread ID which is used to access the data from from the uh, arrays from the data structure using dispatch thread ID x and y coordinates. Now we will look into the related discussion of the research work which is done by the researchers until now. Now first, what is the problem that we are trying to solve here is pathfinding on GPU, because the finding shortest path between source and destination, which is also called as a single pair shortest path problem, is very common in computer games, and a very common algorithm which is used since last few years is A-star algorithm. Now this A-star algorithm improves the efficiency of pathfinding better than the other algorithms, because it just explores a lesser search space than Dijkstra and breadth-first algorithm. Now the pathfinding for multiple agent in parallel is computational intensive problem on CPU because the number of agents increases. The the CPU has a limitation to the number of threads it can create. So we want to try using the very highly multi-threaded architecture of GPU, where we can launch thousands of threads together to solve the problem. So so other researchers since 2008 has looked into the problem and tried to solve using the GPU application. So the very first such implementation came from Belvis at NVIDIA, where he implemented a CUDA based GPU solution for A star pathfinding algorithm. The CUDA is alternative to ComputeShader, which is the CUDA which only runs on NVIDIA graphic cards, and it is also similar to C++ programming language. So where this is a very first implementation of its kind during 2008, and the work highlights that the basic problem is the limited memory on GPU, and at the end they compare the results with the CPU based implementation and achieves a good speed up to 24 times speed up than the CPU implementation. Now another work which is done by Demiller in 2011 is a crowd E framework, which was introduced for crowd simulation, where he uses a hybrid system for pathfinding of a crowd simultaneously. So the approach he uses, first he uses A star to eliminate the the uninterested, or eliminate the area of the map which would not be processed by the algorithm, and then uses the flow fields to compute the path locally. Now the results it shows are interactive rendering of more than 1 lakh agents at 24 frames per second, which is a promising result. After that, uh, Kagnesis in 2012 introduced a parallel hierarchical A-star approach for multi-agent pathfinding on grid maps. Now the approach is a little bit complex. It divides the overall grid into regions or blocks, and within each blocks they apply A star locally. And once all the blocks are computed with the A star and the abstract path is available, the overall path is joined together to obtain the final path. Now this method is a little bit complex and less performance optimization because of repetitive transfer of data between CPU and GPU, because after the processing of each blocks the data is getting transferred from GPU to CPU. Now before we get into the implementation of our algorithm, there are some concepts that we will look into to get a better understanding of the implementation. Now in our algorithm we are using the priority queue with binary heap, which are the binary heap, which are efficient way of storing a sorted list of array. For the open list, we will be using this for open list for A star algorithm. So let's discuss about the insertion operation uh, of for the priority queue. So whenever we insert a particular element into the priority queue, it gets added to the end of the binary heap tree here. So this is, let's say if we insert 5 here, the 5 will get inserted here, and then from there it will try to satisfy the heap condition with the parent nodes. The heap condition is that each parent uh, is it has childs which are higher than the parent value. So in this case 5 gets inserted and it checks for satisfying heap condition, and it found that 18 is greater than 5, so it will swap it with 5. So here the 5 will come up and 18 will come up here. Now again, once the 5 is here, it will check with the parent 9 here. Again the 9 is greater than 5, so it will swap, and then finally 5 has a parent which is equal, so it will not swap here and it will here. So at any time of execution, the priority queue will maintain the heap condition throughout the list. Next, let's see the remove operation. So whenever we do a remove operation on priority queue, it will remove the lowest value, which is the root value. Now once the root value is removed, the very last node in the tree will be swapped with the root item here, and then from here on the heap condition uh, will be satisfied with its child. So the parent node will check for the heap condition that parent node is less than its child or not. So once the 21 is here, it will check if 11 or 9 is greater than 21. No, it's not, so it will replace it with the other its child, and so on until the heap condition is satisfied. So the very the positive thing about the priority queue is that it could be stored just using an array and 1D array. So this is how the priority queue is stored in the array. So the very zeroth item, the zeroth index of the array, here we just store the total number of items or elements in the priority queue, and from 1 we start storing the elements of the priority queue. So the first element goes here 5, and then 9 here, then 11, then 14 here, then 18, then 19, and then 21, and so on. Now this priority queue we will be using in the multi-agent scenario, which means that each agent will be having its own priority queue. So we will look into how this priority queue is maintained for all the agents together. So we will create a open list priority queue, which is a very big array which holds the priority queue for all of the agents. So within the priority queue list, which is open list, the first agent has a block which is equal to map size, which is the priority queue. Now this is the priority queue for agent 0, this is the priority queue for agent 1, and so on. So how we look into this is that the priority queue size is equal to the map size, which is our 2D grid map representation. So let's say for 8 by 8 2D grid map, the number of the map size will be 64. So if we consider rendering, or if we consider the number of agents which are 64, then the total size of the open list queue will be 64 into 64, which is 4096 elements here, elements overall. So let's get into the implementation details. for the for our GPU solution. Now we will implement the two different types of A star algorithm. Not the A star algorithm is similar in both of the type, which is naive, but what makes the difference between two algorithms is how we allocate the thread for the processing of A star. So the first type 1 A star algorithm with one thread per agent is a naive approach, where we allocate one thread to execute the complete A star path algorithm and computes the result. Where in the type 2 algorithm we allocate multiple threads for one agent. In that case, let's say like we allocate 8 threads to for one agent to calculate the final path for A star. We try to use type 2 because it sounds a little bit logical, as we have large number of threads, so we can allocate more thread to compute A star for a particular agent than rather than just giving one thread to for one agent. So in the following section we will discuss these three aspects of both of this algorithm, which is data structure, the program flow diagram, and we will see how we execute each of these type of algorithms with the basic configuration on 8 by 8 grid map and 4096 with the 4096 agents. Now the type 1 A star implementation, which is a naive implementation, uh, the data structure which we are using for type 1 and type 2 are more or less similar, but only for type 2 we have some additional data structure that I will mention when we discuss type 2. So for type 1, here we have the agent input list with the agent structure. The agent structure is something like uint, agent ID, source location, and target location. Now this list is input to the algorithm from CPU to GPU. So this list will be populated from CPU, and the CPU allocate the source and destination for the pathfinding algorithm. Now next is the open list priority queue, which is a empty queue, which will be empty during the start of the algorithm, but during the intermediate state the algorithm will populate this list and use it to read and write the priority queue and manipulate the priority queue for each of the agents, and the data type is simple as uint. Now there is the grid node data structure. This grid node data structure is used for the A star manipulation, where the grid node represent a node within the 2D grid map. So it has x and y coordinate, which indicates which node this particular variable represent. Is it 1 1 or 1 2 on the grid map? Then the parent ID. As we process the A star algorithm, each node will be assigned a parent ID in order to find the final path, or to get the final cost and final path at the end of the algorithms. Then we have a status, where we change the status of this particular node as we process it in the algorithm. So there are these different status which could be used there, which is unread, which will be each node will be set to unread by default. Then open when it is added to open list, then close when it is processed from the open list, and at the end unwalkable if the node is a collision or a wall which could not be walked by the agent. Then we will store some heuristic values: f cost, g cost, and h cost. And finally there is one priority QID which track the index of this node in the priority queue. Now this will be active only when this particular node is on the open list. And finally we will have a fourth data structure, which is search result, where we will store the final cost, the result, which indicates 0 for path not found and 1 for path found, and the source grid ID and target grid ID. So the program flow diagram. Now this is how the program is getting executed, and the data structure are used by ComputeShader. This is the ComputeShader program which is getting executed on each thread, and to the input the agent input list is there, which will carry the source and target data, which will be input to the star algorithm. Then open list queue and grid node list will be intermediate data structure, intermediate list of data which will be used by the algorithm, and finally the output will be given to search result out, and this search result out will be read by the CPU to get the final path. Now let's see how we execute this program flow with the number of threads. So we consider an example of simulating 4096 agents in parallel on a 8 by 8 grid map. So first we on the CPU side we have to assign the default size for the data structure that will be used by GPU. Now this is fixed, this cannot be changed during the execution, so we have to calculate the estimate size of these data structures. So agent list input is generally carries an agent object for each agent, so the size, the number of agent list input elements will be 4096, which is equal to number of agents. Now for open list priority queue, we will have 64 elements for which is a map size, and multiplied by number of agents. Now this factor we already discussed on how to allocate the overall size for open list queue. It will be same for the grid node list, because each agent will need a space, uh, with each agent will need a copy of its own for each map, so it will be 64 into 4096. And finally the search result out, which will be equal to number of agent. The search result will have one object for each agent. Next. Now this is an example of the execution configuration for ComputeShader. So from the DirectX API, we do a dispatch call of 2 by 2, which is 2 by 2 grid, and within this grid each thread group is a 32 by 32 thread group. So the thread group will be having 1096 threads within it, and there will be 4 such thread groups overall getting executed on the GPU. So at the end we will get a 4096 thread running on the GPU concurrently. So this is the exact amount of agents we want to process for the pathfinding algorithm. So this is how we execute the naive approach for A star algorithm, which is type 1. Now let's see the type 2 A star implementation. So as I mentioned earlier, the data structure for type 2 implementation is same as type 1, except that for the type 2 we make use of shared memory array to synchronize between threads within same thread block. So we will see in a moment what this exactly means, but for now let just know that shared memory is limited to 16 KB per thread group. So this thread memory will be an extra data type which will be used by ComputeShader for synchronizing the different threads within a thread group. So because this is a little complicated implementation than the type 1, we will discuss some more aspects in detail. So let's see how the data structure is created. The memory size allocation is same as type 1, as I said, and except the declaration of shared integer shared data, the computer will allocate one instance of array for each thread group. Now what this means is within each thread group there will be an array of shared data which could be only used by the thread within the same thread group. So the shared data instance of one thread group could not be used by the other thread group. Now the compute shader execution configuration is little bit different than the type 1 here. This is because in this approach we are allocating more than one thread for processing of a particular agent. So we are allocating 8 thread for processing of one agent for pathfinding. So in this case our thread group will have each thread group will have only 8 threads. Now within this thread, the thread which has a 0th ID will process the final output for a particular agent, while the other threads here which are 1 to 7 will help to process this particular agent in parallel, but this will not result any output. This will be the only thread where will give the output for the agent which is getting processed. So how we execute is we have so in this case this one thread, we can say that one thread group process one particular agent. So in this case if we want to process 4096 threads, then we will have to dispatch 46 by 46 thread group thread grid here, because each cell in here in the dispatch call will process one agent, and then we will have 4096 threads like this. So this is a snippet of the code uh, for the detailed understanding on the type 2. So here we declare the shared data for the group share like this, which is 3. So and here we do some branching, like the number of threads are 8. So if the thread ID, the thread which is executing this shader, is 0, then only it could execute this path. If the thread ID is 1, then only it could execute this path. And there is a group memory barrier with group sync. Now this is something which is used for synchronizing all these 8 threads within a thread group together. So what will happen is the 0th thread, which is the main thread responsible for processing of a particular agent, will put the current node data into the shared group, and then all the other threads which are 1 to 7 will wait for the 0 thread here to complete this data transfer. Now once the current node data has been stored here, all the other threads will read this data from shared data like the current, and each of these thread will process the neighboring nodes. So let's say if there is an node, and in our case in the grade map we will process the adjacent 8 nodes of a current nodes. So there will be all the eight threads processing on different nodes. Now to illustrate this visually, this is how it looks like: thread 0 and thread 1. Thread 0 will execute this path. The path which looks to thread 0 will be like this. This will be executed by thread 0, and the path which looks to this is how it looks to thread 1 to thread 8. So here it is gid equal to 1. Now for thread 2 it will be gid equal to 2 and all. So this is the main thread, and all the thread will wait here for to reach all of the threads here. Once all the threads are reached here, then only the next path will be processed. This will be done repeatedly until all the nodes are processed. So let's say if the current node is set by the thread 0, then all the threads are waiting here for it to get set. Once it is set and the thread 0 comes here, everyone executes every thread process the adjacent nodes of the current node in parallel. So this is a particular node, so this thread 1 will process the top left node, the next one would process the left node, then the next thread 3 will process the another node. That's how it will work, and all this node will update the priority queue from here. Next, now during the implementation of these algorithms, we came across the very we came across the performance bottleneck which in the parallel execution, which is priority queue. We saw that as the priority queue grew in the size, the performance degrades for the A star execution. So I have been reading some papers where some different approach are used to avoid using priority queue or make efficient use of priority queue instead of making it longer and longer by inserting in the number of nodes at each point in A star algorithm. So as the size as the algorithm process, the size of the queue increases and the insert and remove operation travels through the heap tree, and it takes a longer time. So we came across this delta strapping algorithm, which is for single source shortest path problem, which and uses bucketing technique. This is for single source shortest path problem, which means this is for finding the path to all the nodes in the graph from a particular node. But we saw that this could be used to optimize our priority queue execution. So the bucketing technique that they use is something like they use a bucket and define each bucket with a particular range of cost. So the first bucket here is responsible to store the list of nodes which are within the range of 0 to 20, whose cost is within the range of this, and the bucket 2 is responsible to keep the nodes whose cost is between 20 to 40, and the next one is 40 to 60. Now what they do is they process all these buckets in parallel using allocating one thread to each of this bucket. Now this could be possible only for single source shortest path problem, but this is not appropriate for a two pair shortest path problem, which is our problem. So we can take a technique, a small technique from this adaptation and use it in our priority queue. So our approach is an adaptation of delta stepping algorithm technique. So what we do is we just maintain a priority queue with the node less than cost limit. So at any time in the algorithm we will have a priority queue which is holding node, let's say nodes having cost 0 to 20. That's it. At any time, it could be later on, it could be handing cost 0 to 40, and then later 0 to 60. So how the algorithm will work is, first insert adjacent node to the current node. Like when we process the a star, we look into the adjacent node and then we put that adjacent node to the open list. So we will put it into the priority queue if its cost is less than cost limit. Now this cost limit will be something, a limit which is maintained at a particular time. So we put a particular node to priority queue only if its cost is less than cost limit. Let's say if the cost limit is 20, so we will put a particular node into priority queue only if its cost is less than 20. If it is not, then we just store that node which is having a higher value than the cost limit to a temporary list which is unordered. We just maintain an array and then append the node to the list. Now as we go and process the algorithm, the priority queue will become empty once all the nodes which are less than 20 cost limit in the priority queue will be processed. Once that point is reached, we need to populate the priority queue with the higher cost nodes. So at this point, it will mean when the priority queue becomes empty for the first time, it will mean that the algorithm has processed all the node with the cost which are less than cost limit, which is 20, and it has to process nodes which are higher than the cost limit. So we increment the cost limit factor by from 20 to 40 and double it, and then we traverse to the temporary list and put all the nodes which are having the cost limit lesser than the new cost limit into the priority queue. So the new so what we do is, the priority queue is getting populated with the all the nodes which are less than 40. So this is how it will increment. So the advantages of our approach is that at any time the priority queue maintain the node with lowest cost value and avoid highest cost node in the priority queue. So if we are processing node which are in the range of 20, let's say, of algorithm is executing node with a cost of 20, then it is very less uh, probability that it would directly go to 80 cost node. So we just keep outside the priority queue the highest cost node. Now the size of the priority queue will be smaller, hence faster insert and remove, which is an advantageous at any point, which will help to improve the performance. And then the disadvantage is that we will have to allocate an extra memory to maintain the temporary list. Now this approach is not been implemented because the lack of time, but we see to implement it later on. A real-time rendering pipeline implementation. Now, real-time rendering pipeline implementation, here we have implemented the rendering pipeline for multi-agent simulation on GPU with 8x8 grid map and 4096 agents. The path found by the type 1A star search is input to rendering pipeline use, and then we use the buffer to transfer data between ComputeShader and the rendering pipeline. Now the rendering pipeline is something like this. The ComputeShader will calculate the path for each agent, and this path will be populated into the buffer, and to animate a particular agent in the real world, we will use a ComputeShader to update the location of each agent position and populate it into the buffer. Now this buffer will get fed to a vertex shader, then the geometry shader will expand the geometry to give a shape to the agent, and then finally the pixel shader will give a texturing, and then finally the agent will be drawn into the output scene. Now this will be done parallel for all the agents together in the list. Now the results are here. So we use the basic benchmarking here configuration which are adapted from the published work of Blewitt and Imam. Now we use basic configuration of M0 3x3 size having 64 agents, then 6x6 size map with 1024 agent, and 9x9 map with 4096 agent, and finally the 13x13 size with 16 6 410 41 agents. Now here are our results comparison for type 1A star. Here we compare the result with the Enam results using CUDA, which uses CUDA, and we are using ComputeShader. And here we see that the ComputeShader implementation has a overall better result than the CUDA implementation. And the graph shows that at the most of the time, as the number of agents increases, the overall execution time is not as much as the CUDA implementation here. Now next we compare the type 2A star implementation, where the GPU time we see that the GPU time for type 2 implementation is higher in our case for the ComputeShader implementation. This is mostly because the very divergent path followed by the thread group in the threads, and the way we populate the threads is not recommended by GPU programming experts, because every thread follows a very divergent control flow. So finally we implement the two type 1 and type 2 A star pathfinding algorithm using ComputeShader. Now, up to our best knowledge, this is the first implementation of A star using ComputeShader, while Blewitt, Inam, and other researchers has implemented using NVIDIA CUDA platform. Our type 1 result outstands the CUDA results, while our type 2 results shows the gradient performance. And finally we also propose a bucketing approach to maintain the priority queue for performance optimization, but because of limited time we could not implement the proposed approach. Thank you for listening to the presentation. If you have any question, you can forward it to my email ID. Now after this presentation I will show a little demo of the real-time execution of the multi-agent pathfinding on GPU. Thank you very much.